next talk about it will be about the proof minimization given by Omri. Okay, thanks.
Great, thank you for the introduction. So I'm Omri, I'm advised by Professor Katz. I'm from the Hebrew University. And in this talk, I will present our project to develop a proof minimization algorithm for neural network verification. And it is a joint project of researchers in the Hebrew University, of Amherst College, and Stanford University. Well, I think at this point, it's almost redundant to say that neural networks are everywhere now, and they accomplish great results in many fields. Some of them are safety critical, but unlike traditional software, neural networks are opaque functions, and even the people who train them, they don't really understand the meaning of the internal parameters. And this combination could be very dangerous because neural networks can behave undesirably. It will be very hard to predict. And of course, this could be potentially dangerous. And what we keep in mind is, as an example, is what we call an adversarial examples. We have a classifier. Is that okay? Okay, that classifies images. And it correctly classifies some images. But if we perturb this image by a little, in a way that the human eye cannot see, then it makes the classifier go wrong. So we would like to ask, well, can we rule out the possibility of error, or at least have some guarantee to find one if it exists? And to address this question, the verification community has developed a variety of verifiers based on a variety of techniques, SMT, abstract interpretation, MILP. So we already have a bunch of verifiers, but they're human-made programs. And as such, they're prone to bugs, to implementation errors. They typically use floating point arithmetic, and therefore, they make mistakes as well. And these mistakes can also be exploited to make the verifiers to get wrong results. And of course, if the verifier is wrong, well, then what's the point on verification? So one might try to verify a verifier. That would turn out to be a very complex task. So instead, what one can do is to enhance a verifier with a proof production capability, as is often done in SAT and SMT solving. The verifier would not only return a result, it will accompany the result with a proof of the result, and that proof could be checked and witness the correctness or reveal the errors made during the verification process. But there are also problems with these proofs. Currently, proofs are eagerly storing lemmas that were learned by the verifier, and that might lead to very large proofs and might be unnecessarily large. It will slow down the checker, it will cause memouts. And what we focus on this paper is on an algorithm to analyze this proof in order to remove unnecessary lemmas. It's a process that's also known as unsat core extraction, again, in SMT and SAT solving. And it is doing so by two main processes. First, it removes lemmas that were learned but were not used. And second, it removes lemmas that were used but are shown to be unnecessary. And altogether, it reduces proof size by almost 82%. So this is in general. But before going into depth, we need to cover some background. And I'll start on background on neural network verification. So to formally define the problem, we have a neural network. We define some input property and output property. Then the verification problem is a decision problem of deciding if there exists an input that satisfies the input property, but the corresponding output would violate the output property. And if it exists, we say the problem is satisfiable, and we treat this satisfying assignment as a counterexample, because it's a counterexample for the output property. And otherwise, we say it's unsatisfiable, and we treat it as a compliance of the network with the properties. And many verification algorithms then reduce this problem to a constraint satisfiability problem, as we have in SMT. And for this talk, we will assume for simplicity that the properties are linear, quantifier-free, and that the network employs piecewise linear activation, and specifically ReLU. Even though our work works with any piecewise linear activation. The ReLU function is very simple. function. It's the maximum of the input and 0. And it has two phases, the active phase, which is the identity for positive inputs, and the inactive phase, which is constant 0 for negative inputs. And the result of this kind of reduction that we'll soon see an example would be to solve this kind of constraint satisfiability problem. We would look for an assignment of variables that would be in the kernel of some matrix. It will be bounded from above and below. And there will be value constraints on a subset of the variables. So let's have a look at a simple example. We have this neural network here. It has 2 inputs, 1 output, and 3 hidden neurons. And we have this very, very simple property. Then the reduction to the form that I previously shown you is this kind of, it's in this form. I don't want to go into too much into depth of the technicalities on how this reduction works. It's unnecessarily complicated. But the idea is that this represents the original network and the property. And for example, you can see that each one of the hidden neurons that have the value activation function is broken into 2 variables, the backward and the forward. And that the tableau here, the large matrix, it expresses the linear combinations of the neural network. So for example, B1 is the entry of V1, and it has to be equal x1 minus x2, which are the ones that we see over here. So we will now focus on this kind of problems rather than this formulation, because this will be easier for us to analyze. So you can see that this structure induces linear and piecewise linear constraints. And together, the verification algorithms would search for a satisfying assignment for the linear part, using LP solvers for the linear part, and case-splitting approach for piecewise linearity. And schematically, it looks like this. The verifier would invoke an LP solver. It would search for a satisfying assignment for the linear part of the query. And if it finds that there is none, then there's no solution to the overall query. Otherwise, it will find a satisfying assignment. But then we need to check whether it satisfies the piecewise linear part as well. And if it does, then we can conclude satisfiability, and we have a counterexample in hand. Otherwise, the solver is inconclusive, which means that we might need to split into subqueries. We pick a piecewise linear constraint, break it into its linear pieces. Each piece has its own query with additional linear information, and then we can repeat the process again and again. And that induces a tree structure to the search. We call it the search tree. And note that the query is unsatisfiable if and only if, for each subqueries that we tried, we got into unsatisfiability, because otherwise we would find a satisfying assignment at some point. And one of the main questions that I'm often asked, well, couldn't that tree be exponential? The answer is yes, it could be. It's possibly unavoidable because it's an NP-complete problem for ReLU networks. However, it can still be solved in reasonable time, as is often done in unsat. And that's it for the background on neural network verification. I'll continue to proof production, but if there are any questions, I'll stop. If not, I'll continue. Great. So a few words on proof production. First of all, we're dealing with a constraint satisfiability problem. And as such, proving satisfiability is rather straightforward because we can use a satisfying assignment. However, proving unsat is more complicated. And again, we have the complexity theoretical result to ground it. But what we can do is we can produce a proof tree that concretizes the search tree, in which every leaf, every node represents a case split that was done during the verification process, and every leaf corresponds to, has the proof of a contradiction for the corresponding subspace. And now we will cover exactly what each one of the parts here means. But I'll start with how we can prove the unsatisfiability of the leaves. And remember that leaves are proven to be unsatisfiable by the linear part. So we have a classical result from linear algebra in our hands. And specifically, we have this lemma called the Farkas lemma. I'm sure most of you are familiar with. It has many variants, but the variant that we're using is a variant that is relevant to the linear portion of the queries that we already saw. And in this variant, it tells us the following. Either there exists a solution, satisfying assignment for the variables that satisfies all the constraints, or there is a refutation in the form of a vector such that it creates a linear combination of the tableau that could never be satisfied by variables in these bounds. And not only that it exists, we can also construct it during a verification process. And the idea of using it as a proof is that it gives us a direct result, a direct algorithm to get to the unsatisfiable configuration, even if the solver has explored many linear combination of the constraints. So checking the proof is much, much easier than finding one. And we go back to this example. Again, it is too technical, but we will cover this, this proof of unsatisfiability, this W, and we can see that if we take this vector and we multiply it in this tableau, we get this combination of the variables. And if one wants to check the proof, it generates this linear combination, and then it uses the lower bound for variables with a negative coefficient and the upper bound for variables with a positive coefficient, and it needs to check that it's a negative number. So it could never be in the kernel of the matrix. And if it indeed it is negative, we can say that the contradiction is correct. So we use this vector in order to prove the unsatisfiability of the leaves. But of course, we're not dealing with a linear problem. We're dealing with a linear and piecewise linear. And as such, there are more complications to that. And one of them is what we call bound tightening lemmas, which are lemmas that are deduced based on bound propagations on the ReLU functions. And those cannot be captured directly by a single Farkas lemma that proves the unsatisfiability of all of them. And instead, we prove them sequentially, one after another. So for example, let's say we have this ReLU connection between these two variables, and we learn as a fact that f cannot be larger than 5. Then it means that we can also deduce that b is not larger than 5 as well. And we can prove it by using a Farkas vector that proves the first result, what we call the invoking bound, and then a proof rule that captures this form of derivation. And after we do so, we can use this as a proof of the corresponding lemma. So we'd have these lemmas as well. So after we have, we cover the lemmas and we cover the proofs of a contradiction, we can have a look at how a proof leaf would look like. It will have a sequence of lemmas learned one after another. And in order to check it, we need to check that, that indeed this vector yields a result that allows us to derive this bound. And then the proof rule is indeed corresponds to a proof rule of a ReLU bound derivation. And we do this sequentially to all the lemmas, and then we're ready to verify the contradiction. So this is how we prove and we check the proof node. And if we go to the proof tree, we need to traverse the whole tree. For each node, it might have its own lemmas. We need to check the correctness of these lemmas. And for each split, we check whether it corresponds to linear pieces of a piecewise linear constraint. And then at the end, for node leaves, we repeat the lemma checking, and we check the contradictions. So we're finally ready to think of proof minimization, because as you can see, it's rather complex structure, and it has it might have too many lemmas that are learned, but are not necessarily necessary. So what do we do? At first, what we try to do is that we go back. We perform a backward analysis that tries to tell us whether a lemma, even though it was learned, it's not really used during proof checking. So we start from the contradiction. We analyze the dependencies of the lemma. We ask which lemmas are used in order to derive the contradiction. And we repeat the process recursively until we reach the input data. So more technically, remember that unsatisfiability is deduced by computing this linear combination, and we need to ensure it's negative. And when we do so, we take the upper bound of variables with a positive coefficient and the lower bound of variable with a negative coefficient, and then we get a number, and if it's negative, then we're done. And note that other bounds that were not used are not really relevant for us. So we start by marking all lemmas as not relevant, and in the backward process, we mark each lemma that we detect as relevant, and delete all the rest. And of course, each lemma has its own vector, so we can repeat the process recursively in a very similar manner. So if we go back to the example from before, we have a proof of a contradiction for our running example. And earlier, we saw that this linear combination uses B3, and B3 has a learned bound using this lemma. And it doesn't use the lower bound of F2 because we only need the lower bound. It's a negative number, which means that the contradiction is not derived by lemma 1. And if we repeat the process for lemma 2, we also see that it doesn't need lemma 1. So we can remove lemma 1 from the proof, even though it was detected. So that's cool, but we ask, well, can we do better? And the answer is yes. The algorithm might include lemmas that are used, but are still unnecessary, because, of course, used does not really mean necessary. And we further use a proof refinement that refines the proof by removing a maximal number of unnecessary dependencies, where the maximal set is defined in a local term. We'll shortly see what does it mean. Again, going a bit more into technical details, what we do is we go back to our computation over there. We compute a linear combination of the variables, and we need to ensure its negativity. But of course, ensuring its negativity, it's not just a matter of a yes or no question, because we can also measure the quantity of the negativity. And the idea is that we call this quantity delta, and this delta could be very far from 0, but the proofs, the lemmas that are used in the proof are not really necessary to this negativity. Even without them, the contradiction would be negative as well. So the idea is to remove the lemmas by their contribution to this negativity to the current analyzed vector. And we remove, of course, we greedily remove them by their ordered by their contribution, and it's a knapsack problem. So we're guaranteed to have maximality in the number of edges that we remove from this directed acyclic graph. So we can go back to our example. And in our example, we're not just ensuring the negativity, we also state that it's -2. And we also state that lemma 2 decreases the value of B3 only by 1. So its contribution is -1. And -1 is larger than -2, so it's not necessary. If we remove lemma 2, the contradiction here would still be with -1. So we can mark lemma 2 as unnecessary as well and remove it in the proof analysis process. And therefore, we're left only with one contradiction without the two lemmas. And it's only the tip of the iceberg. There might be more heuristics for dependency removals to remove more and more lemmas. Some of them appear in the paper. And actually, I think for this, I will not go into too much into depth, but the idea here is that there are a lot of things that we can still cover. So going into evaluation. We've implemented this on top of a neural network verifier called Marabou, which we developed in our lab in Stanford and Amherst College. And we evaluated our method over 6 benchmarks, most of them using the ReLU function only, but other also including different activation functions. And we asked 2 questions to measure the effect, to measure our work. The first is the effectiveness, how many lemmas we removed from the proof. And the second is the performance overhead that was needed when we created this, we applied these algorithms. And this is just one example of the ACAS benchmark, which is very common in neural network verification. On the left, we can see the size of the proof after minimization and the size that could have been if we haven't applied minimization. We can see that the different heuristics that we checked, they didn't matter much, but we were able to remove large percentage of the number of lemmas. And we can also see that there are also a few benchmark examples that we could not have verified without minimization because we got mem outs and so. And on the left, we can see that we have a cactus plot for the running times, and we can see that there is no much difference. And overall, across the benchmark, we saw that between 37 and 82% of the lemmas were removed. For most of the example, it was more to the 80-something%. And the overhead was between 7 and 20% of verification time. So looking ahead, there are three main things that we're looking to do. The first is to explore minimization heuristics and see if they are more effective. The second is we'd like to extend the proofs to incomplete methods, so we can use this method for a larger variety of neural network verifiers. And lastly, and this is a thing that we're actively pursuing, is to use this minimization algorithm for CDCL. And the idea is that minimization algorithm is a core algorithm for deriving clauses, and we hope to use that in order to get a meaningful and scalable CDCL algorithm for neural network verification. Then to conclude, I presented an effective proof minimization algorithm that is used in neural network verifiers, and it has relatively low overhead. We have the paper and the code available, which also have an artifact in the submission. And I hope it was interesting, and I'd be happy to take any questions.
Yeah, so I don't know if you've seen, there's this work on kind of verifying the proof verifiers, right, for SAT. I think the KKML has been used for this. So is that something how much work do you think that would be to kind of formalize, let's say, theorem prover or something like that to the proof checking?
So it's actually a really good question because it's another project that we're working on, and this is supposed to support that. This work should support this one. It's a difficult task if you want to do it with a new proof checker. But it's something that we managed to do, and it's a collaboration with Harriet Watt and Southampton University. We published it in the last ITP, but it doesn't support these theory lemmas. And another thing that we could try is to try to convert these proofs into a standard that could be used that has its own verified checker, and then use that checker. So that will be another challenge. I think it would not be as difficult. Another interesting point is that this proof minimization makes the checking process much easier. Thank you.
Thank you. I was curious about when exactly this is done, this proof minimization, whether it's done after the verification and the proof is actually produced by the tool, by the verifier, or if it's somehow inbuilt in the verifier and you can perhaps do some more reasoning about it and eliminate some lemmas for perhaps future use and so on.
It's a good question. It's a point it's in the paper, but I haven't touched it. The idea is that we remove lemmas during verification, and we try to do it as early as possible so they won't accumulate. And what does it mean to do it as early as possible? Whenever we finish with a leaf, we can remove the lem of that corresponding leaf. Whenever we finish with the two children of a node, we can finish with the node, and so on. So we do it, I'll say it semi-lazily, during verification and after we finish the corresponding leaf or node.
Yeah, so it can also help with the memory consumption of the verifier.
Yes, and it does, and we saw that in the evaluation here. So here, it's hard to see here, but we also checked the baseline, and we saw that most of these examples were solved by our verifier with proof minimization, but they weren't solved with the baseline because they reached mem out. And we were generous with memory.
Okay, thank you.
Thank you.
Thanks. For small unsat queries, maybe you can compute the exact optimal minimum. And do you know how close your heuristics get to that?
We haven't tried that. It's very hard to get a small unsat thing. But yes, it's a very interesting question, both theoretically and practically.